I am Rico Mariani, and I'm here today to talk to you about performance and building a performance culture in your team and some things you can do to improve the performance of your managed libraries and applications. I thought I'd start maybe by asking, doing a little quick survey of the audience so I could get a feel for where you all are. Maybe if you could raise your hand if you've been working with managed code for a year or more. Well, that's a good chunk. And maybe, so say 6 months or less at the other end. 6 months or less, okay. So it's about, looks like about 25% at about 6 months or less, and about 50% at a year or more, and somewhere in between there. So that's a good mix. Okay, well, I usually like to start the talk by just telling you a little bit about myself, so you have a clue who the heck I am and why you might want to listen to my advice. So I told you my name already. I'm Rico Mariani. And in a few weeks, I'll be celebrating my 16th anniversary at Microsoft. And so 16 years is a long time to be here. My first 7 years were in the developer division, and I worked on a variety of different products, starting with C6. That's not Visual C6, mind you, that's before the Visual. From C6 all the way up to about VC3 was about when I left. And then I did 7 years in MSN on a variety of projects there, starting with Sidewalk, which some of you may have heard of, and maybe some of you haven't. And I learned a bunch of different things about operational systems and servers and backends and all reliability and all kinds of cool stuff. And then about 2 years ago, I returned to my roots and came back to the developer division, and I took a position as a performance architect on the CLR. And that's what I've been doing for the last 2 years, and so it's been quite a ride. So that's, you know, me in a nutshell. And so today I want to give you some tips about performance. So let's move up. Okay, the first rule of performance is measure. There's actually very few rules when it comes to doing hardcore performance because so many things can change out from under you. But really, it all begins with having an understanding of what your customer needs, what's going to be important to your success, and being rigorous about measuring whatever it is that's important to you on a regular basis. Now, I like to say if you're not measuring, you're not really engineering. Okay? Engineering is a quantitative discipline. So any sort of approach that you take that is about, well, let me guess, or let me see what the best practices are, or whatever else, people have, called that anything from creative coding to maybe software craftsmanship, but it's something short of engineering. Okay, so the quantitative aspect is what makes it an engineering procedure. So once you've decided that you're going to measure, a bunch of good things happen for you, and I think that's really kind of, one of the big benefits there. The moment you say, okay, well, I need to measure because I want to be engineering, I'm going to want to measure. Okay, so the next question is, well, what should I measure? Okay, well, right there, already you're asking yourself a great question, because in order to decide what to measure, you have to get in touch with who your customer is going to be and what's important in any given scenario. Okay, so you'll be saying, well, does my customer care about space? Does my customer care about time? Does my customer care about disk footprint? What is it that my customer cares about anyway? And is that always going to be the thing he cares about? Or does my customer care about one thing in some scenarios and something else in other scenarios? And how am I going to, do a good job of getting in touch with what my customers are going to need out of the performance of my product? All of those kinds of metrics sort of force you down an excellent path of understanding and process, okay? Because you'll be able to take those metrics and milk them, as we'll talk about, during other parts of the software development process and not just, the performance analysis. Okay, so the first rule, measure. If you haven't measured, you haven't done your whole job. The second rule is do your homework. Okay, now again, let me, contrast this to another kind of engineering. If you were going to put up a building, say you were a civil engineer and you were going to put up a building, you have to make a lot of choices about how you're going to go ahead and put up that building, right? You're going to have to decide, well, how many stories should it be? What should the placement be? Blah, 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 blah. And in order to make those kinds of decisions, you're going to have a superior understanding of what it is that buildings are made of and what are the big issues surrounding the building of buildings, okay? And so a simple one is you might have to understand what parts of your building you're going to have to make with steel and what parts of your building you're going to have to make with aluminum, okay? Now, in order to make that decision, you have to be very familiar with the properties of steel and aluminum. If you're not familiar with the properties of steel and aluminum, it's going to be impossible for you to make a good choice. And so you're going to end up using a material that's too strong or too weak or too expensive or too whatever it is in inappropriate places. Okay. Now, in the software world, this translates to two sort of popular phenomena, both of which net you disastrous performance. The first popular phenomenon, and this is like, when I say popular, I mean I see this like once every 2 weeks. The first popular phenomenon is you build your service in such a way that it depends, no service, your library, it depends on a system or an assembly or some other kind of thing that you fundamentally can't afford to use. Okay? This is classic. So for instance, suppose you have a very strong startup time requirement such that you have to get your little thing up with a marginal cost of no more than, say, 5 milliseconds. Okay? With a 5 millisecond budget for your startup time, you can rule out all kinds of things that you might want to use just by running the dir command. Okay, you can look, say, dir, that one's a meg. Oh, guess I can't load that one. Okay, because there's no way you could even soft fault in that much memory in 5 milliseconds. Now, on the other hand, if you're up at, at like 75, 100 milliseconds and you're going to be running longer, or maybe, startup time isn't an issue for you, then you have a great deal more flexibility. Okay, and, the number one assembly that people misuse in this category is system.xml. People are always woeful about system.xml. Okay, but system.xml is a perfectly fine assembly with a perfectly fine design point. And it offers a variety of different services that you may find useful, and that indeed we try very hard to make easy to use, but that doesn't mean that they're appropriate to use in every context. Okay? If you need to be up in, a few hundred microseconds, probably you don't have time to load up system.xml, so maybe you need another solution for getting your initialization state. Maybe you shouldn't use, say, an XML initialization file. I'm picking on the XML system again because lots of people pick it up and that one's frequently abused, not because I particularly find what they've done distasteful. It's just you need to understand the design point of what it is you're going to pick up. Okay, so phenomenon number one, people take a dependency on a system or service that they fundamentally can't afford. Phenomenon number two is people pick up or use an algorithm that fundamentally lets them down. Okay, so for instance, suppose you need to do some sorting, okay? And so you have this, complex mess of stuff that you're going to have to sort, but you don't want to think very hard about how to do the sort, so you choose like a simple-minded sorting algorithm, and it turns out that the sort that you chose behaves abysmally in the situation that you needed. Okay, now if you do a little bit of homework, you'll understand what the properties are of the various sorting algorithms, and you can choose one. Maybe you need a stable sort. Okay, maybe that means you're going to have to pick heap sort over quick sort, even though the top performance of quick sort is better than the top performance of heap sort, but heap sort is stable, so you need to know which one is stable. Or maybe you went really cheap and decided you were going to pick up something even less sophisticated than that, and then you found yourself in really big trouble. So in both cases, okay, you could find yourself in a situation where you've taken a dependency you can't afford. You can find yourself in a situation where you're using an algorithm that's letting you down. Both of these are problems you solve by doing your homework. Understand the basic properties of the things you intend to use. Don't make excuses for having used a technique or relied on a service that then lets you down, because it is your responsibility to make sure that your raw materials are up to the job. Okay? It's definitely not the responsibility of the guy building the raw materials. Although, to be fair, we'd like to partner with those people sometimes too, because it could be that whoever's building that component wants to rise to the challenge of your application as well. And so if you can, make the underlying goods better for everyone, that's a good thing too. But that should be done with a plan as well. Okay. There's no more rules. Rule number one and rule number two are about the only things that I will give to you as sort of mandates in the performance world. You must measure, you must do your homework. Failure to do those two things is a recipe for disaster. Everything else I'm going to tell you today has a bunch of caveats on it, as ifs, buts, and quid pro quos. You just never know. Performance work is plagued with powerful secondary and tertiary effects that frequently dominate the thing that you thought was the problem, and result in, well, surprises. Okay, so the best engineers will find a way to do the experiments they need, do the measurements they need in an efficient manner, and quickly discard the losing paths. okay, because there'll be plenty of them, and by measurement, by prototype, or by whatever other kind of technique, we'll be able to hone in on the winning techniques comparatively quickly and not spend a whole lot of time on the losing techniques. So you should plan for the kinds of risks that you'll encounter when doing performance work. Okay, only rule number 1 and rule number 2 are mandates. All right, so given that we have this whole sort of measurement culture and doing our homework culture, what kind of techniques could you use on your team to improve sort of the overall culture, okay, and get people following a process that's likely to lead to substantial successes? Okay, well, I have sort of this 3-step plan that I use, and I've gotten the CLR team to adopt it in many areas, and more people are getting to adopt it. And I think it can work for a variety of different teams. So I'll put this forth as kind of a starting point for you to have more perf culture in your team. Now, the first step is budget, okay? Whatever it is that you're going to build needs to have a budget. Not having a budget is saying, well, if we're building a feature, not having a budget is like saying, I want this feature at any price. Okay, well, that's a load of bunk. I mean, I don't know what that is, okay? But clearly, whatever it is that we're building, if it takes 7 days to boot, probably we can't afford it, okay? So, somewhere between the 2 milliseconds that the customer will tolerate and the 7 days that I just mentioned is the actual sort of budget that we have to build this feature in. Now, how do we get a budget? We don't get a budget by looking at the code. Budgeting is not a directly technical exercise. Budgeting is an exercise wherein we get to know our customer. We talk to our customer and we say, well, we have this new feature we'd like to build, and we think it would offer these and these different services. Okay, and we go and we look and see how are people using our product and how would that impact their work cycle or impact the way that they use our product. And they might tell us, well, yeah, we like that feature a whole lot. Why, we'll get all these substantial productivity gains. And that's great. The sad part for us, those of us doing the budget, is rarely do customers come back to you and say, yeah, we're willing to pay 2 milliseconds and 60 kilobytes for that feature, but no more. I don't get a whole lot of that. I get, well, yeah, that sounds good, but we really need startup time to still be good, when they'll say qualitative things like that. During the budgeting phase, we have to take our customers' qualitative remarks and we have to turn them into quantitative budgets for our feature. Okay, or for our whole release maybe, because we may say, well, we have this series of productivity features that we're planning to add, okay, and they're going to impact startup, but our customers still need it to be snappy, and we did some usability tests and we find that they start feeling like it's sluggish at around the 30 millisecond mark. Okay, great. So that means we have 25 milliseconds for our whole enhancement suite for this release. Okay, so then we can say, okay, of the 25 milliseconds, how are we going to spend it? We have these 6 features. Okay, well, this guy is going to need some startup time for this fancy initialization he needs. Maybe we can budget him 10 of that, so 25. These other 3 guys don't need very much. We'll give them, 4 milliseconds each. And what do we got left? Well, maybe we'll use that for cushion in case something comes in beta. But at the end of your planning cycle, you will have taken whatever qualitative feedback you had and whatever understanding you had of the customer and turned that into quantitative resource constraints, sometimes on time, sometimes on memory, because it might be working set. How big a box do these customers have, right? At what point are we going to start swapping? Sometimes they're on working sets, sometimes they're on private pages, sometimes they're on throughput, sometimes they're whatever it is that's important to your customer. Remember, we were thinking about what we had to measure, and those metrics that we chose for our product, right, should tie very tightly back to the budgets that we're then considering during our performance planning. Okay, so step number 1, we did this budgeting exercise. We haven't even looked at the code yet, right? Step number 2, we have to plan, okay? And what does that mean? We have to be in a position where we can say, here is a way that I can deliver this feature, okay? I have a design for this feature, and it is substantially likely to be within the budget, okay? And notice the words that I chose, substantially likely. Okay, a question that I often get asked is, well, Rico, how do I know how much planning to do? I mean, I could plan and prototype and, just keep planning and planning and planning and never get any actual work done. I mean, at some point we got to actually code the thing. Surely, you don't want the plan to be so comprehensive that it's more complex than the code was. And, well, of course I don't. So the planning phase is about managing your risk, okay? So we have to say, okay, what is it that we intend to do? How much work is that? how much planning should I do given that the work that's at stake? If I have a 2-man year kind of effort to get this feature in, probably it's worth it to spend a few weeks, you know, doing design documents and maybe making some spreadsheets to model the performance and getting a feel for what are the pivot points or what are the important metrics and, you know, what is going to be performance sensitive and what isn't, and getting a very good understanding. We do all of those things to manage the risk. Now, at some point, we're going to start feeling, okay, I've planned this pretty much to death. I'm really, you know, very confident that I can execute on this plan at this point, okay? How confident do you have to be? Well, if it's a 2-man year effort, pretty confident. You know, if it's, on the other hand, a 2-day effort, well, you know, if it doesn't go so well, you know, it's not the end of the world. So the risk is going to depend on the nature of the product, the nature of the deliverables, you know, the nature of the customers, okay? And at Microsoft, sometimes we take pretty aggressive bets, okay? And other times we're like kind of shy, all right? And it's all going to depend on the context and the importance and the intergroup dependencies and other kinds of things, okay? You may find that you can get good guidance as to how much risk you should be taking from, you know, your management or your partners or your customers, okay? But taking some bets is a good thing. All right, now remember, we were taking a bet. So at the planning phase, we had a plan that was substantially likely to succeed, and we had an understanding of what the risks were and, you know, what our performance metrics should be looking like. Okay, step 3 is verify, right? Remember, we were taking a risk, could go wrong. Okay, it's very important if it does go wrong that we not inflict it on the world. Right? We went through the budgeting exercise for a reason. We wanted to understand what it is that our customers would tolerate. Where is it a good value? At some point, your customer would rather have the speed, right? Or the space, or whatever it is. You know, so if you're adding 7 days to startup, they're going to think, you know, maybe I didn't need that smart coloring quite so much. I don't think it's worth that 7-day startup, right? Okay, so if you're within your budget, you're great. Okay, if you're not within your budget, it's probably time to cut bait, or maybe go back and recalibrate, or, you know, maybe you can whittle away the feature and still deliver something that's of value. Okay, but at that point, you'll have to recalibrate. Now, hopefully, you're not in a situation where the only verification you intend to do is at the very end. Okay, there should be checkpoints, right? I mean, it should have been clear fairly early on that things were not going terribly well. Okay, and only rarely will you find yourself at the very end and say, oh no, now we're at the end and the very last thing didn't work out and now I got to throw the whole thing away. That would be a very bad situation to be in. Not a good way to get a big bonus. Okay, so thinking about your plan, your budgets, and your verification steps helps you throughout your entire life cycle, because that plan is going to tell your testers what they need to be looking for. It's going to help you on the scheduling phase. It's even going to help you after you're out in production, okay? What performance counter should you have? What things should you be including in your debug logs, okay? If your customer's having problems in the field, what questions should you be asking him? Maybe you could say, hey, what's your startup time looking like? You're supposed to be in the 50 millisecond zone. Oh, you're at 75 milliseconds. Oh, something very bad is going on. Which one of our assumptions must have gone wrong? You know, if you're at 75 milliseconds, that's out of our design point. So it can help you everywhere from a test plan to an operations manual, and for feedback in the next version of your product, because of course you'll want to look at those constraints and see, okay, now next generation of hardware, new set of features, what's a good trade-off, let's look at our old dimensions. Milk the plan, okay, because you're going to spend a lot of time looking at it. Don't just do it and think about it and throw it away. I mean, okay, sometimes all the planning you need to do is a few, you know, numbers on the back of a napkin, okay, because it's that obvious that it's going to be easy, and, you know, the requirements are, you know, maybe very, well, very easy to meet, okay. For some internal tools, they're one-offs, whatever, you know, good enough, okay. We need to be able to go through our files a couple times in a batch, has to run overnight, okay, easy stuff, all right. So don't over-plan, okay, because that's bad too. But other times, we're going to want to take lots and lots of very careful steps. Okay, so 3 steps: budget, plan, verify. All right, so some things that you will see in your organization if you're doing a good job. Okay, these are sort of healthy symptoms, if you will. Okay, if we look at some of these things, you'll say, okay, well, if I am having good performance practices, I should be seeing that I have, you know, well-defined goals. Okay, and I should have benchmarks that I'm running on a regular basis. Okay, I should have maybe gauntlets that are protecting my check-ins. Okay, so that on every check-in, I have a certain set of minimal sort of bars that I have to meet, and maybe those can evolve over time. Okay, so I should be seeing things like that. Okay, if I'm not seeing things like that, maybe I should be getting a little bit worried, you know, because my perf can get out of control with any check-in. The thing about performance work is, well, software is like any other complex system. Entropy tends to dominate it, okay? So unless you're taking regular sort of controlled steps, you're going to find that just by entropy, things are going to get worse over time, right? People make check-ins and they're not all thinking about performance. And so when someone checks in a thing and they're not actively thinking of performance, you know, the statistics are it's more likely to hurt you than help you. And that tends to compound. And so by entropy, things will tend to just sort of decay. Okay, so it's very important to be tracking that and making sure that you have a process to help you to identify where those things are happening. Now, the tighter that, the bigger your team is, the more people you'll have working and the greater the entropy is. And so the more important it'll be to be able to get right back down to the source of that one check-in that caused a big problem. Okay, and be able to find it in a sea of noise. If you have a comparatively small team, it might be adequate for you to run your performance benchmarks maybe once a week, okay, maybe once every few days, because the amount of work that happens in the course of a week isn't so bad that that it would be very difficult for you to go back and find out what your problems were after 1 week of working. Okay, but on the other hand, you know, on the CLR, we have, what, 70-odd people checking in things. Okay, if we weren't watching the performance on every check-in, we'd go mad at the end of a week. How many check-ins is that? A few hundred check-ins? You know, oh, there's been a regression. Good luck finding it. Okay, so you need processes that are going to help you control that entropy. There should be unit testing that developers are doing before they check in, right? Okay, and that could be part and parcel of the BVTs or not. Okay, and that should involve performance. Now remember, we had a plan. Okay, and we knew what our metrics were, and we should be measuring those things to make sure that we're delivering on those metrics and that we're on track with our checkpoints. If all that culture is following from your scheduling practices to your planning practices and your feature delivering practices, you'll be milking that plan, and it'll be very clear to your developers what they're supposed to be doing at what step, and it'll again be clear to the testers what they're supposed to do, because if we're supposed to be at checkpoint X and the performance is supposed to be at a certain level, they'll know what metrics they're supposed to be at, and they won't be guessing as to how to test the perf, right? Because everyone will agree. One last thing, especially when we're doing performance improvements, it's frequently the case that we can't get there all in one bite, nor would we want to because of the risk that's involved in getting there all in one bite. So, for instance, on the CLR, we wanted to go down from around 40% of the pages in an assembly being private, okay? And I'll talk a little bit more about private pages later, but we were up at about 40% private pages. We wanted to get that number down. We want to go down as low as 5%, okay? Great, so that's great, 40 down to 5. But can we do that in one milestone? Probably not, okay? That would be some pretty insane work happening there. So we want to have both goals in mind. Okay, for any given milestone, we're saying, okay, well, this time we're going from 40 down to 35, 35 down to 25, 25 down to 15. Okay, so we have staged goals for particular milestones that are very achievable, and people can understand what they're supposed to do and can feel good about those successes. But we also keep that long-term goal in mind, because when people are thinking about adding new, we want them to be weighing against the long-term goal of 5%. Okay, so I mean, 5%. Private pages could be like 2 pages out of out of the total. Okay, 2 might be that 5%. And so if someone's thinking of doing something to add 1, okay, we want them to be thinking, oh, it's supposed to be 2 when we're at 5%. I'm going to add 1. That would make it 3. That's really bad, right? Whereas if he was thinking about adding 1 while we were still up high at 40%, it might not feel so bad, right? I mean, I didn't do the math in my head, but it'd be a lot more than 2. Right, it'd be more like 16, and so he's adding 1 to 16, and so 16 plus 1 equals 17 doesn't feel nearly so bad as 2 plus 1 equals 3. Okay, so it's important to have both that short-term focus and the long-term focus in your goal setting. Okay, all of these things are applicable. I mean, I talk about them in the context of the CLR, but all of these things are applicable to just about any kind of managed code development that you might encounter. Okay. I guess the next point that I want to make is that we have to strive for simplicity in our designs. And I think this especially in managed code. People tend to go crazy when they pick up managed code. And they think, oh, great, managed code, it's so easy. I can add all these features. Look at this. Oh, this is so much fun. And they're having fun. And their class supports this method and that method and the other method. And it's polymorphic and it has subtypes and supports 22 interfaces. And, you know, they just go completely nutso. Okay, and I guess it's kind of cool that you can go nutso and your head doesn't explode, you know, doing the development. But at the end of that cycle, you end up with this thing that's so general purpose that it could do everything. I mean, it could do, you know, it could do things that you never even dreamed that it could do. And this is not inherently a good thing. Okay, for several reasons. I mean, the first reason is your poor customer picking up this class that you delivered is going to look at it, and he's going to feel like he's picked up a Swiss Army knife that has like about 800 blades on it. He's like, I just needed a screwdriver. Where is it? You know, and he's opening it up. Nope, pliers. You know, and big giant things are springing out. Right? I mean, you could imagine this Swiss Army knife where he keeps opening up blade after blade after blade, looking desperately, you know, for like the knife, and like, nope, screwdriver, nope, hammer, nope. You know, what is this? I don't even know what that is. Put that back in. Okay. Now we have things to help manage this. I mean, our IDE offers IntelliSense, thank goodness. Okay. And so, you know, we can help you sort through that screwdriver or that Swiss Army knife with the 500 blades or 800 blades or whatever it is. Okay. But fundamentally, if we'd made a much smaller Swiss Army knife with just the blades we needed for our particular application, the overall utility to your customer would be a lot higher. Okay, and then people say funny stuff like they say, well, I wanted my class to be very reusable, Rico, you know, and so there were all these other cases it needed to handle so it was well-rounded and reusable. And I look at them and I say, reusable? You weren't even usable, much less reusable. I mean, no one would ever want to pick up this thing, okay? So you first have to be usable, then you can be reusable, okay? And so specializing or understanding at least what your core competencies should be and making sure those are very easy to find, and then making sure that those secondary things aren't completely contaminating, you know, the primary things, both in terms of complexity to your user and in terms of performance, because you know when you add those 800 other features and you make the thing all well-rounded in general, you're probably going to get an internal structure that's a whole heck of a lot more complicated, okay, than it otherwise needed to be. I mean, a really popular one is people decide that they have to add synchronization to their class. So, you know, it has a mode where it's lockable or not lockable, and they say, well, you know, you can have all the updates be atomic. And okay, well, that could be useful, but it comes at quite a price. Okay, all the people who are going to use your class are going to have to choose whether or not they're taking the synchronized version or the not synchronized version. Maybe a whole bunch of methods that otherwise didn't need to be virtual are going to be virtual now, so there could be subtypes. So that's going to prevent inlining. And so there's all this collateral damage just in case someone on the off chance that they needed a synchronized version could go to your class directly. And then the alternative was he could synchronize it himself, you know, with a locking primitive, and maybe he's even in a better position to synchronize it himself because he knows where the atomicity needs to be, and you didn't. You're just guessing. Okay, so I don't know. You know, that's just a classic thing that people do. Keep in mind that every time you add a new feature, there's collateral damage associated with adding that feature, both in terms of complexity and in terms of performance cost. And a simpler design is sort of inherently better, right? Whenever you add new features, they start at a net penalty, and they have to justify themselves. Right, both in terms of value to the customer and in terms of performance in some cases. Okay, so going back to the planning phase, measuring, doing your homework, if you focus on what your customer needs, be customer driven, and put your emphasis where your customer puts it, you'll tend to naturally do the right thing because you won't want to spend a whole lot of time adding GWiz features, and you won't want to spend perf on the GWiz features. You'll want to stick to your core competencies, and that's a good thing. Okay, here's another little one. Many people quote me this line, and most people don't even really know the context in which it was given. But it's who's heard the phrase, premature optimization is the root of all evil? Raise your hands if you've heard that phrase. Okay, well, a good number of people, but not everyone. Okay, it was made popular by Don Knuth, although he was quoting Tony Hoare. Tony Hoare, by the way, is the inventor of Quicksort. Okay, so premature optimization is the root of all evil. Well, okay. It's hard to stand here and say that optimizing prematurely is a good thing. I mean, you know what, I should get 10 milligrams of premature optimization daily? You know, I don't even know. I mean, obviously, premature anything is kind of bad. I mean, it's hard to think of a sentence that begins with the word premature that's a positive thing. Okay, so you know, maybe lottery winnings, premature lottery winnings. You know, I was trying to think of something, and it's very hard to think of anything. Okay, so premature is bad. Okay, but people use this phrase, premature optimization is the root of all evil, as an excuse not to think about performance at all, okay, in their early planning. Okay, so let me go back to an example from before. Say I wanted to code a sort, okay, and so I'm a guy and I've got the premature optimization is the root of all evil religion, and so I say, oh no, I'm not going to invest in my sorting algorithm just now. That would be premature. What I'm going to do is code it up the easy way first and then make it fast later, right? Okay, that's the religion, okay? All right, so they write the easiest sort that they can think of, bubble sort. Great, got that bubble sort in there, it's nice and easy. Then later they find out it's too slow. Big surprise there. Stunning development, bubble sort, about the worst sort that isn't completely stupid, okay? Just wasn't up to snuff. So they got to replace it. So they go, you know, because they're obviously a fan of Tony Hoare, because they're quoting him. They go and they pick up quicksort. Okay. Now, let me ask you. Okay, if you are in a position where you needed to substitute the bubble sort algorithm, and I'm using bubble sort as kind of the proxy for, you know, the problem here. Okay, if you were substituting your bubble sort with a quicksort, okay, how much learning did you get out of coding up the bubble sort? You going to just tune it up? You're going to, oh, I'll just, you know, tune it up, right? I'll turn it into a quicksort. You're not going to tune it up. You're going to throw it out, right? I mean, there's not a darn thing in common between those two things except for the greater than test. The bubble sort is going pitched out the window, okay? And you're basically writing a whole new sort from scratch. And you spend a whole lot of time maybe, you know, living with your quicksort and planning around the quicksort, living with your bubble sort and planning around it, or not thinking about what you need to be doing. And now at the end you find yourself having to discover the quicksort, okay? Now, if you're lucky enough that you can reach off the shelf and have Mr. Hoare save you, okay, that would be a good situation to be in. But a lot of times there is no off-the-shelf thing that you're going to plug in. Your design is fundamentally flawed, and you at the last minute are going to have to go back to the drawing board and figure out how the heck you're going to do something that's plug compatible with the quote easiest way that is going to fit into your overall system. You can easily find yourself doomed, okay? So Tony Hoare wasn't talking about making sure that your design is sound and that you've chosen the right algorithm when he said premature optimization is the root of all evil, okay? He was talking about, don't go and, like, without even looking at a profiler, you know, start to hand tune the assembly language that's associated with your sorting routine. Okay, that's completely ludicrous, right? But do make sure that you have the right algorithm in place and that you have a plan in place that lets you be substantially likely to succeed against your performance goals. That's performance planning. Remember, when we were doing all this planning, we had to be quantitative, okay? If we weren't being quantitative, we weren't being engineers, okay? It's not a case that we're being premature by insisting on some numbers, okay? We're failing to be engineers when we fail to ask for quantitative metrics that help us make choices. We should be able to quantify the risks that we're taking, and we should be able to quantify the performance characteristics of what it is that we intend to build. Okay, if we're not doing that, again, we're on this, oh, I want this feature at any price philosophy, and that's a losing strategy. Okay, so don't let a nifty slogan like premature optimization is the root of all evil stand between you and greatness. Okay, so I think I've given you probably all the performance culture you can stand at this point. The next few slides are a little bit more technical, and we'll be talking about some ways that you can maybe get more mileage out of modern processors and how that sort of relates to managed code a little bit, and some other kinds of things you might think about, and also some planning exercises that you might want to go through and how you might want, you know, what approaches you might want to take. But in terms of the dogma, I guess I'm done. So my next slide is about locality, okay? Now, many people don't think about locality, well, raise your hand if you even know what I mean when I say locality. Okay, well, that's not very many people. That's like maybe 20% of the audience. Okay, so locality refers to how close together things are. okay? So if I have a bunch of objects and I allocated them, or I made a data structure and I've allocated over time, if they were all allocated pretty close together in time and I was careful about how I made my data structures, all the pieces parts will tend to be close together in memory. And that's a good situation on a modern processor. In fact, in addition to rule number 1 and rule number 2, about the only thing that I'm really willing to predict is that on a going forward basis, microprocessors will get faster at a faster rate than memory will get faster, okay? And so what that means is that having your things be close together and be, readily cacheable and so forth will tend to become more important over time rather than less important. Okay, so I want to have data structures that are fairly straightforward, okay, that don't have lots of pointers flying all over the place, okay? And there's many reasons for this, okay? One of the reasons is, of course, that I want to have good performance, okay? And another reason is that I want to have fairly simple data structures that, my mom could understand, okay? Or maybe not my mom, but at least Mort anyway. Okay, so think about your memory as being divided into pieces parts, very much like the way you think your disk is, okay? When you think about how to lay things out on disk, you think, oh, well, there's sectors, and I have to go, and I want the related sectors to be together, and I want to have not too many seeks, and so forth. So let me show you a couple of pictures. Okay, so here's an example of a data structure that's maybe less than good, okay? And the funny thing is people draw these pointers and they don't really think about, what it is that they're drawing. Like, for instance, look at that pointer between A and B, okay? At the very top there. See how that's a short pointer? It's just little. See, it's just a tiny, cute little pointer. Well, it can't possibly be very far from A to B with such a short line between the two. They must be practically next to one another. Okay, but compared to A and C, now, see, there's a long pointer there between A and C, long arrow, see, so that's a long pointer, so C must be pretty far from A, so that's how you read this diagram, right? The short lines mean that the pointer is nice and close, right? And the long lines, no, that isn't true at all, is it, right? Every pointer could be a total disaster, and in fact probably is, unless you take pains to make sure that that doesn't happen. Okay. Now, one of the things you can do in managed code, okay, and it's fairly straightforward in managed code actually to improve your locality. One of the things you can do is make sure you allocate as many of these things as possible at the same time, okay? If you allocate things close together in time in the garbage collected world, they tend to also be close together in space. And furthermore, as your program runs, things that were allocated fairly close together will tend to get squeezed closer together because the free objects that might have been between them will tend to die and things get squeezed together because our allocator compacts over time. So the situation will never be worse than it was when you started and might actually get better if you allocate things together. Now, if you're using unmanaged systems, I can assure you the situation will never be any better than it was when you started because none of these objects are ever going to move, okay, because you get the address and you get the address and that's the address forever. Okay, and it could be arbitrarily bad because you don't know. I mean, if B is slightly bigger than C, then you might have got a different heap for B than C because there was a free block of the right size over there, and but C was over here, and then A was nice and small, so it was up there, and so who the heck knows where any of these guys are? You might have to go through all manner of gymnastics to arrange for these guys to be allocated together. That's why people do wacky things like custom heaps and whatever else in the unmanaged world. In the managed world, forget all that. The main thing you have to remember to get good locality is to say, okay, whatever I'm going to use together, I try to allocate together, and I'll get pretty good behavior. Now, I have a little way of scoring these diagrams I'm going to illustrate, okay? And you can all practice along with me. Have your developer, okay, or if it's you, draw the diagram on the board, like this one. And every time you draw an arrow, do that. Okay? So A, B, C, D, E, F, F, ow. See, and then you'll be able to tell how good your data structure is by how much your hand hurts, okay? So if your hand doesn't hurt very much, you're in pretty good shape. Now, I've seen these things go across multiple whiteboards, just pages and pages of stuff, and I think, wow, I mean, what feature are we building here for this spaghetti structure? It's pretty awful, okay? And, remember, if you're building a library, you especially want your structures to be simple because some poor guy's got to understand them other than you, okay? And probably they'll be exposed. So less of this, more of this, okay? See that nice, big, fat, thick arrow? See, that's an error. That's a pointer that is carrying lots of information because it's pointing between those two nice big blocks, you know. And so I have blocks that were allocated in the middle of arrays, and I have nice guaranteed continuity between my F's and A, B, C's, and D's. Now, okay, the truth is liable to be somewhere in between, and I'm not saying never use pointers. Okay, I mean, obviously, turns out pointers are kind of handy. Okay, so you know, don't never use pointers, right? Just remember rule number 1 and rule number 2. Okay. Think about what you're doing. Think about the simplicity that you might gain by consolidating some of this stuff, okay? And don't gratuitously be allocating and adding things that are, you know, for special cases. You have to be sure that when you're adding a new feature that it's paying its way, okay? It has to be a good deal to add that new feature. If we always said no to adding new features just because it was going to slow things down, we'd never add anything, right? So we are willing to slow things down or make things fatter or bigger or whatever else, but we do want to be giving our customers a good deal. They have to feel like they're getting value for the space or the speed or whatever it is that they're trading off. Okay, so here's a few examples of these kinds of things that I ran into in my travels through managed code in the world. The first one was in the Avalon codebase, and I was looking at that quite a while ago. And here we had an example of someone using a general purpose IEnumerator structure in the middle of their message dispatch. Okay. Now people probably know the for each pattern and and IEnumerator, but I mean, have you stopped to think if I have a for each within a for each, the inner for each is going to allocate an enumerator on every pass through the outer one? Okay. So there was a case where a poor little guy, and he was a perfectly smart guy, but he just temporarily, lost his mind. It's okay. It happens to the best of us. Okay, temporarily lost his mind, did a for each inside of a for each inside of the message dispatch loop. This loop was responsible for 1/3 of all the allocations in the Avalon scenario in question, okay? And like we were talking about iterating an array list in this case, and it had like 3 elements in it. It was really, kind of pathetic. Okay, so the whole thing could trivially be replaced by a for loop and have no allocations at all. Okay, so what's important? You have to be looking at how you're using the memory, okay? If you were measuring, you'd see this instantly, right? You'd go, look, oh, holy mackerel, what am I doing there? Look at all these enumerators. Oh, I see what's happening. I've nested for eaches. I don't need to do that here. That's, that enumerator's not paying its way, so let me get rid of that. Okay, other cases where there's multiple levels, I think I've talked about this several times, multiple levels of indirections to handle extensibility cases that are just extraordinarily taxing, okay? Sometimes it's important extensibility cases, but we have to make sure that they don't penalize the main path. So, for instance, sometimes the accessibility path, okay, can be it's important. We have to get that right. It has to be in there. So we don't, not do accessibility paths, but we do say, okay, well, I have to make sure that the accessibility path is something I only pay for when I'm using the accessibility features, okay? At which point it is definitely earning its keep, right? That's a good deal. The guy who's using those accessibility features, boy, is he glad they're there, okay? And we want to be there for that guy. But we don't want it to be the case that we're paying the cost of the accessibility path on all the normal, easy paths that don't need that extra work, okay? Right, and that's true of, accessibility is an easy one to pick on maybe, but that's true of any kind of exotic feature. Sometimes we have things that kick in, they're operating system specific, they're user specific, maybe the user likes this customization feature. That's fine, but in the default case, we don't want to be incurring a lot of cost, okay? So keep in mind that your feature should be very much pay for play, okay? All right, another kind of thing that happens. People lose their mind in kind of, wacky ways. When you're writing a sorting function, a comparison function that's going to be used in the context of a sort, you really don't want to be allocating any memory in there, okay? So, for instance, if you want to take a bunch of strings and sort them by, say the characters that occur after the first comma, okay? One way you could do that is to call string.split and get, the field that happens after the first comma, they're comma separated, okay? Now, if you did that, though, it turns out string.split returns an array, right? So where do we think this array came from? How much homework do we have to do here to determine where that array came from? Pretty much it had to be allocated on the heap, right? Okay, and then all the members of the array, well, they're strings too, right? Okay, so where do you think they came from? Heap, right? Okay, so now should anybody be surprised that string.split did some Alex? Probably not, right? Okay, so if you are surprised, well, you know, it'd be helpful to look at a trace of the run, and you know that will unsurprise you. Okay, but if you're writing, you know, a comparison function or a hashing function, and you think to yourself, I'm calling this function, and oh, it's going to do Alex. Wow, can I afford to do this? I mean, it seems like, oh, it's just a little comparison function, string.split, oh, that's pretty efficient. But comparison functions, they get called n log n times in the context of sorting, right? So we can't afford any Alex. Now, it turns out that the old-fashioned way of doing string comparison, you know, with the strings in place, like where like in C++ you do stirchar or something like that to find the first comma, and then, you know, you could do stircomp or sternComp, you know, to compare the appropriate number of characters. You can still do that in managed code. It still works. String.compare, it's still there. You know, index, it's still there. It still works. You know, that whole tried and true, been working since the late 50s. Still do that. And you know what? It uses no memory, and it's fast as heck. Okay, so like I totally recommend no memory and fast as heck. I can't emphasize enough how if you got that free and cheap and easy, and you know, and the split isn't even particularly easier to read than some of the other stuff. So if you're writing a hashing function, okay, and actually a good tip. If you're wondering whether you're writing a hashing function, you need only look at the name. If it includes the word hash in the name, probably you're writing a hashing function. Okay, so usually it's called, you know, hash something. So if you're writing a hashing function, probably a bad idea to allocate any memory at all. Okay, and you know, yelling at the garbage collector for being slow, given that you allocated during a hashing function, not going to get you a whole lot of sympathy. Okay. Similarly, if you're writing a function that includes the words compare, includes the word compare in its name, good chance that you're writing a comparison function, and probably it'll be called in the context of sorting or other searching, and it too needs to be extraordinarily frugal. So be double careful in those cases. Very smart guys that I deeply respect, just, you know, they lose their mind temporarily. It's you know, I don't know what it is. It's just, you know, they do this and then they don't measure, and afterwards they, you know, they make that Homer Simpson sound, you know. Okay, so think about your data structures, think about their shape, think about whether they need to be growable or extensible in some wacky kind of way, and pay for what you need to pay for. Okay? Again, it comes back to doing your homework and measuring. You will make mistakes. That's okay. We all make mistakes. You know, notice I never mentioned the mistakes I made during this little talk. Okay. Well, that's because there's too many, and I don't want to bore you all, and I only have an hour to talk. Okay, but I guess the trick to being you know, a successful performance person is kind of the same as the trick to successful photographers, right? You know, successful photography is about taking 500 pictures and then showing your friends 3. Right? And you say, oh, look at the pictures I took, and you show them 3, and he say, wow, what a great photographer you are, and you're like, yeah, I'm not showing you the 497 bad ones, you know. So that's okay, all right? And perf work is substantially like that too. When you're looking, you're going to have losers, expect it, make sure you're ready to call those, and don't be too ashamed of them. But if you're there doing your homework, that'll help you to make better decisions more often. Measuring your results regularly, you'll be in a great position to cash in on the wins and throw away the losers. Okay. So I've got 3 more slides. They're kind of dense, and mostly they're here. I put in all these words so that you would have them to refer to when you looked at the handout later. I'm not going to even talk to all of this because, you know, we don't have time for all that. But the next 3 slides, I'm going to talk about some things that you might be targeting, okay? Some common things that people might want to be doing in terms of improving their performance or planning for their performance, and how you might go about doing that, okay? Now, the first one is working set. Okay, now, okay, let me do another audience survey. How many people know what working set is? Raise your hand if you know what working set is. Okay, great. Oh, that's a lot more people than I expected to raise their hand. About like 70% of the people. Okay, so with reducing your working set refers to the amount of memory, of course, that the process that the operating system rather has committed for use by your process, okay, to get your job done. So obviously if you can use less memory, that's a good thing because it frees more memory for use by other applications. As I'm fond of saying, just because the box has 2 gigabytes of memory in it doesn't mean you get to use it all. Okay, because the user probably has other things he wants to do too. So you should be always thinking about being frugal. Okay, so I'm trying to plan for the working set of some new feature that I intend to deliver. Okay, great. So how do I do that? Well, it turns out working set has 2 big drivers, and they are, surprisingly enough, code and data. okay? And there's, a variable mix there, okay? To get a handle on the code that's going to be added, you need to think about, well, how much code am I going to be writing to support this new feature? And frequently, that's something that you can estimate, right? You can say, well, how much code is it compared to other kinds of things? In this project, what's the sort of bytes per line of code, typical ratio? So I can do a variety of fairly straightforward pen and paper exercises that will help me to get a handle on how much code I intend to add. Okay, then I have to think about, okay, well, so that's the total code I'm going to write. How much of that is running and where is it running? Because when I'm measuring working set, usually I'm not thinking about sort of, universal working set. I'm thinking about in the context of scenarios like startup or like, project build or whatever the heck it is, okay? So then you have to think, okay, what is the marginal impact of this code that I'm writing on startup or on the build, okay? Is most of the code not active during that time? Or did I have to sprinkle a lot of new sort of tests in the existing code that are going to get dragged in kicking and screaming? So again, there might be a part of the cost that's not pay for play. So I pay the cost whether I use the feature or not. There might be costs that are more pay for play. But in any case, I can go right to the size of the code and say, okay, here's kind of what my contribution is likely to be. And that will give me good guidance as to how my working set might be affected. And from that, I can make a plan that's substantially likely to hit the budget, where I can say, here's how much code I'm going to add. You can see it's a total of, it's going to be approximately 200 lines. So that turns into 20K of code, so and so many pages. And so we can afford that according to our budget. That's a good situation to be in. Okay? So once I have an idea what my budget is, then the next thing I can do is think about, well, what unit tests should I be putting in place to gate those, and how should I trend that, and do I want to plug into some benchmarks that I already have or not, or what have you. But I can play a lot of games with that. Okay, so working set planning basically based on code size, and then symmetrically on data size. Again, when I do the data size, I can look at it in two ways, right? What collateral damage am I going to have to do to the existing data structures to fit in my new feature? And what new data is completely unique to my new feature, and what does that look like? And I should be able to add up all those bytes, right? It's not so hard. I can do prototypes if necessary, but I should be able to get a very good handle on how much data I'm going to have to add to support my new feature. Okay? And at the end of those two exercises, I'll have a pretty good idea what my working set impact is going to be. Okay, the second biggie is private pages. Okay, so how many people knew what working set was? Raise your hand if you know what private page is. Okay, less people. Okay, more like 10% of the people know what a private page is. Okay, there's two kinds of memory. The kind of memory that can be shared with other processes, and the kind of memory that can't. Okay, and actually, it doesn't matter so much if it can be shared, but actually if it is shared, because sometimes we have pages that are theoretically shareable, but that won't be shared because there's only one instance of your program running. So the shared pages tend to be things like the code, okay? If there's 3, 4, 5 copies of your library in memory, and you're running a library, okay, all of the 5 copies will share the very same physical memory to hold the code, okay, to the extent that we don't dirty it. Right? And so we do, we're trying. I was talking about that earlier. We're trying to be very good about not touching those code pages so that they can be shared. We like shared pages because shared pages, you kind of amortize the cost over all 5 copies of your library, right? Like when the second copy of your library starts running, it pays much less than the first copy because, all the shared pages are already resident. So we don't have to, hit the disk for them. We get lots of benefits. So we like shared pages. We don't like private pages nearly so much. So the biggest source of private pages in a managed application is the GC heap. That's the one you control. There's other sources of private pages, but they're for my team to sweat over, and we do. Okay? And I really would rather you not sweat over those nearly so much. Think about what you're going to be putting on the heap. How big is it? How often is it going to get touched? Okay, and of the data structures you could be building, which ones of them are pay for play? It's a recurring theme. Do I build those data structures all the time, or do I build them only when they're needed? Did I have to make modifications to existing data structures and make them bigger? So just, on the off chance that this new feature is being used, or do the existing data structures already, handle the extension just fine? Okay, so to the extent that you are adding new features that have very little cost in terms of data that is associated with them when they're not in use, you're in very good shape. And when you have features that have to do a lot of damage to existing structures or require complicated extensions or generalizations to the algorithm, you're going to find yourself hurting a lot. Okay, so here's some rules that talk about some tools you might consider using and how to measure it and so forth. But basically, this one is all about the GC heap. Okay, so think about what data you're going to build, think about the overall bytes, and you can translate that to private pages. And that's big goal number 2. Number 3 is startup time. A lot of people talk about that one too. This slide's even denser than the others. There's 2 big cost drivers for startup time. And it turns out that most of the time, the code that runs at startup time is fairly straightforward code. This isn't always true, of course. Remember, the only thing that's always true is measure and do your homework, right? But frequently, startup code is fairly straightforward. It doesn't do a lot of complicated looping and ifing and other kinds of jazz. So the main cost associated with startup code has to do with getting that code loaded, okay? And so there's 2 kinds of code of costs. For shared pages or pages that are in the cache, you're going to pay a very small penalty for loading those in, okay? And you can think about charging yourself about 1 microsecond. It varies, but in round numbers, charge yourself about a microsecond for every 4K of data that you intend to bring in from the cache. And I said code, but actually it's true of any data. If you have initialization files, if you have registry data, if you have, well, wherever it is, wherever it's coming from, if it's in the cache, charge yourself about a microsecond a pop. Think about how much computation you can do in a microsecond, right? On a modern processor running at a couple gigahertz, that's several thousand instructions, okay? All right, category 2 is the really expensive one. If it's not in the cache, it's going to cost you more, like on the order of a millisecond for every 4K you're going to drag in, okay? And you can plan for that as well, okay? But at 4K, at 1 millisecond for every 4K, you can see how you could easily blow a 10 or 20 millisecond startup budget, with very few pages. Okay, and don't be fooled. It's not just the code, right? Any I/O. So if you're looking at a config.xml file, woohoo, okay, that config.xml file might not be hot, especially if it's specific to your application. Okay, so that means disk faults, and so that's going to eat up a lot of your budget. Okay, so think about what you're going to drag in to the process to get your code started. And if you do have exotic algorithms at startup time, then of course you're going to have to budget for those too in terms of execution time. But it's a pretty good approximation to start with. What code am I going to drag in that's hot, and what code am I going to drag in that's cold? Or what pages am I going to drag in that's hot, and what pages am I going to drag in that's cold? Because again, it doesn't matter whether it's the code or whether it's the data. All right, so that's startup time, and those are kind of the big 3. A 4th one for us on the CLR is the cost per app domain. And that one might be relevant to you as well. On my blog, there's a more detailed version of this document that talks about that goal as well. Okay, so just to wrap up, remember that you need to understand your goals. If you don't understand your goals, you can't possibly do a good job on them, okay? Think about rule number 1 and rule number 2. Think about the cost of everything you do and facilitate your homework. Use performance culture. Performance culture in doing your job. Budget, plan, and verify. That's all I have for you today. And I've got a little bit of time left over for questions. I think before I wrap up, though, I'd like to plug some of these links. You can find some good material on my blog that's out on MSDN. If you do nothing else, go and look at msdn.microsoft.com/perf. That's our performance and scalability pag, and especially Chapter 5 is on managed code. It's got all kinds of information, detailed information on good patterns for using our classes, from the collection classes to synchronization to just practically everything you ever saw. So I strongly recommend Chapter 5 of that PAG, and internally DevDiv CLR Perf has good resources as well, including some videos and other flavors of this talk too that have stressed other different points.